the real power of LPs for approximation algorithms comes via the duality theory. And so I'm going to try to convince you of that first in the abstract, and then we'll see examples tomorrow. What's this about? So let's again take a step back. Why did we use LPs for these optimization problems? Well, we wanted a lower bound. Say it's a minimization problem, just to fix the language. We could, from the relaxation, get a lower bound on the optimal solution for our problem by taking the fractional solution. Now, there's another technique to get that, namely dual problems, where you also get somehow a lower bound on the optimal objective function. It has some benefits, as you'll see later. Let's first see what this works like. And this I don't want to rush too much. Because I think is if you've seen it once the right way, you never need to remember the rules for dualization. So here's our fictitious LP from before. The goal is to somehow bound its objective value. So it's a minimization problem. We'd like to have a lower bound for how good can this possibly be. So we want a lower bound for this 7x1 plus x2 plus 5x3. But of course, subject to the constraints. Otherwise, it wouldn't be a solution. And so one option is we can take this objective function, and we can make, because the x's are non-negative, we can make some of the coefficients smaller. That makes the overall value smaller. In particular, we can take, instead of 7, we can take x1. Instead of plus 1, we can take -1. And instead of 5, we can take 3. And then I've essentially reproduced this first constraint. So because x is feasible, this got to be bigger than 10. Ta-da! I've proven a lower bound on the optimal objective value subject to the constraints of 10. Right? All I've done is I've rewritten the objective function using the constraints. And what I've done here is I just lowered the coefficients for each of the variables from 7 to 1, from 1 to -1, from 5 to 3. Now I could try, let's try to make use of the second constraint, right? If that worked so well, maybe we get something better. And I could try to get to this. But it doesn't work for x2. So I can't really use that second constraint in the same way. Also, the lower bound we would get here is even weaker, so it's not interesting. But there's also kind of a hurdle here in using this trick. Now, what else could you do? These are inequalities, and inequalities can be added up. So if you add up those two, you get 6x1 plus x2 and 2x3. These are component-wise smaller than our bound here. So I can take the sum of the two constraints. Let's call this A and B. I'm doing A plus B. Then I get, what did I say, 6x1 plus x2, 2x3. And the sum of the right-hand side is 16, which is better than my 10 from before. So I've made some progress. Aha, so how far can I push this? In general, I can multiply these entire constraints with some arbitrary numbers. I cannot just take the sum. I can take any linear combination, right? So I can multiply the left and right-hand side with some arbitrary value. Aha, but maybe not arbitrary because I have an inequality. So I certainly would want that my my y's are non-negative, right? Okay. Also, to have a useful statement, I cannot produce this middle part where I'm making any of the coefficients larger for a lower bound. So I need to make sure, for example, for x1, I want to make sure that y1 plus 5y2 is below 7, right? Otherwise, I don't get this bound. And I get the same for the other two variables. So minus y1 plus 2y2 should be below 1. And for x3, I get this constraint with 3y1 minus y2 less or equal 5. And what's the lower bound I get from doing the linear combination? It's going to be 10y1 plus 6y2. And so I can pick any such y's, and I might as well pick the highest lower bound. That's the best I get. Okay? Is the process clear? And see how this, just by the numbers, nicely corresponds to working superficially on the LPs. The coefficients of the objective function here turn into the right-hand sides of the inequalities. The right-hand sides of the inequalities in the original problem turn into the coefficients of the objective function. If you've had inequality constraints here, that means that the multipliers you put to the inequalities have to be non-negative, otherwise you flip the sign. But had there been an equality here, you could have multiplied by a negative number, it would have been okay. And so you get constraints on the variables here come from the constraints in the original problem. And in a way, vice versa. If you have greater or equal here, then you can allow the coefficients to drop. If, say, x1 would have been allowed to be negative, then I can only get a valid bound if the coefficients are equal to 7. Okay? So you're playing a game where you try to get a lower bound for the objective function, and that game turns out to be another LP, and that's exactly the dual LP. I know that most or all of you will have seen dual LPs in some sort, but oftentimes it's just, here's the definition, deal with it. Whereas you can very, very logically derive all the rules for dualizing LPs that way. If you write them in standard form, then it's also quick to memorize if you prefer. If that was your original problem, the primal LP, then the dual will have this shape. Min turns into max. The coefficients here, they just swap and A gets transposed. And these are the generalization I mentioned on the example already. Okay? Now, so far, this was kind of by example shown what we're trying to do. This is just the definition of, if you start here, that's the dual problem. Whatever you prefer, you can show for any feasible solution in the primal, respectively dual, the pair of those, they always give you a bound for the optimal for the objective function values. Namely, for the minimization problem, you get a higher thing than for the maximization problem. If you imagine, oh, it's not bounded. So there's the values for the cost function. Then you have the CTX and BTY. They somehow lie here, and you always get that they're ordered this way. That's called weak duality, and it's a simple consequence of the definitions. You can prove it in general on this normal form as follows. If you take the dual constraint, A transposed Y less than C, transpose the inequalities. These are element-wise inequalities on the vector, so you can transpose that, and the inequalities couldn't care less, I guess. So C transpose is greater or equal A transpose Y, the whole thing transpose, and then, you know, the rules for transposition means you flip the product inside around, so it's YTA. And then you can just rewrite the objective value of the primal. Start from here, you replace C with that CT here. Then you have this associativity. You change the order of the parentheses. Then you use the primal constraint on AX. And that gives you a bound on of B here, and then that's a scalar. It's just a number. So if you take YTB or BTY, it's the same. That's weak duality. Okay, so you can always get this bound, and that's almost by definition. We've chosen the LPs so that this is the case. The more exciting part is that you can, for LPs, show that the exactly optimal values are the same. They coincide. Formally, if you have some optimal solutions, X star and Y star for the primal and dual respectively, then the objective values match. That's a bit more linear algebra to prove, so I'm not too keen on doing it. We're just going to use this as a fact. And there's another cool thing that's useful for designing algorithms sometimes. This is a characterization of when a pair of solutions is optimal. Namely, so some feasible solution, X feasible for the primal, Y feasible for the dual, are jointly optimal if and only if these two conditions are true. So for every index j, either xj in the primal is at 0, so it's kind of tight on its non-negativity constraint, or the corresponding inequality in the jth constraint in the dual is tight. So here you have equality, and that's not helpful, I guess. You always have equality on one of those two constraints, either in the primal or in the dual, and you have this for all j and for all I. They're playing opposite roles. And they're called complementary slackness conditions because you cannot have slack in both of the constraints and be optimal. And in particular, this is an if and only if. All right. If you want to take the complexity angle, you can say for LPs, not interlinear programs. All of this is just for LPs, right? Not for the interlinear programs. For normal LPs, the fact that you have strong duality means that you have a yes and a no certificate, primal and dual variables. And so we know that the decision problem is in NP and in co-NP, but we already know it's in P, so maybe that's not so surprising. For the interlinear programs, much of what's on this current slide breaks down, but the weak duality you can still rescue. That stays valid, and you can dualize interlinear programs in just the same way, using the idea of lower bounding the objective value.